And so now we'll talk about the uniform continuity. So again, I talked a little bit about when we were reviewing for the exam. In general, when discussing continuity, delta depends on epsilon and let's say on the C, on the C at which you were trying to establish continuity. We were proving whether or not, like say, i.e. we proved, say that a function was continuous at a point C, and if the function was continuous on all points of C, we said the function was continuous at all points of C of a set, let's say of a set A. We said the function was continuous on A. So if we check somehow those continuous all the points of a set A, and we kind of looked at each specific pointer, if we could somehow do that and then find that there was continuous, we said it was continuous on A. And so now we have something a little bit more called uniform continuity, which says when we're finding our delta, unlike before, it's going to depend not on epsilon and C, but just on epsilon. And so now this is the way it's generally stated. And so let me do this 5.41 definition. Let A be a subset of real numbers. And let F be A to R. We say F is uniformly continuous on A. Now, again, we're kind of talking about the whole set. If for each epsilon greater than 0, there exists a delta greater than 0, such that if X and U are in A are any numbers, satisfying X minus U less than delta, then F of X minus f of u is less than epsilon. So it's going to be uniformly, again, when we talk about uniform continuity, it's always going to be on a set, you know, on say the whole set E. And so you have to be able to pick an epsilon and say, excuse me, given any epsilon, there exists a delta greater than 0 such that if x is from x and u are in A, satisfying this, then this is less than epsilon. So let's go back to our favorite function, 1 over x, since that kind of is helpful to illustrate a lot of these ideas. So let me take, I don't know, let's just pick, say, something, let's just maybe consider f of x equal 1 over x. But let me pick a specific interval, let's say on, say, 0.1 to 1. Show that f of x is uniformly continuous on this set. So now again, you have to pick you're given an epsilon, and it has to work. The epsilon you pick has to work for any point in this interval. So keep that in mind. Once again, we'll sort of do some scratch work. Again, if you can jump right to the proof, that's fine. I like to kind of scratch just to get some ideas what's going on. And so here we're going to say, again, the idea is, and it kind of relates to something I did talk about before. For something to work, if we're given an epsilon, for something to work for all values here, we're going to have to make it work for the maximum value in this interval. So, so for uniform continuity, find maximum value of f on the interval. You might want to kind of think that, and of course that's going to be, since it's going to be increasing, it gets smaller, that will be f at what, 0.01, huh? That's going to give us the largest value on the interval. And so it's going to be 1.01, and with that could be 100, huh? So keep that in mind. And so once again, this is still the scratch work, let epsilon be greater than 0. Again, and we want this, this to be able to work for any two values on the interval. And let's see here. So what are we going to have to do? We're going to have to say, again, we want this less than our epsilon, and x minus 1 over u. We're going to have to do it this way. Ux, sorry, we'll have to make a common denominator, just realize that. Ux, so make a common denominator, sorry. So I just multiplied this by u over u, this by x over x, and then we'll go u minus x divided by ux like this. And then we could say, we want this now, we could say this is going to be less than or equal to u minus x over 0.01 times 0.01, like this. And then we want u minus x. And what is that going to be? 1, 2, one more, like this. And then we want this to be less than epsilon. And so then we'll do u minus x is going to be less than or equal to 0.0001 epsilon, like this. And then this is going to be our delta. Sorry about that. I was thinking about bounding the function. I messed that all up. So yeah, so because of course I had bounding in my mind, but we're still looking for the u minus x, so we had to kind of go through here. And so let's do the proof. Let epsilon be greater than 0. Choose delta to be 0.123 epsilon. Then for all u and x in A such that u minus x is less than epsilon, we have 1 over x minus 1 over u is equal to ux minus x ux equal to u minus x over ux. And now this is the key step right here, is because this is always going to be less than u minus x times 0.01, and then this is always going to be less than delta 0.01, and that's always going to be less than this thing up here, 0.001 epsilon 0.101, which is equal up like that. Sorry about that. For some reason, my brain was thinking towards putting bounds on, but we're still doing continuity. So any questions on that? Now, again, so see, this was the key step right here, is that, and we'll get to do it next time. But see, we couldn't do that if our interval went down to 0. See, if our interval went down to 0, there would not have been a number that we could put in here to say for sure that that's less. And we can talk about that next time. For anyone who can't be here, is there a particular question that you wanted answered if you can't be here on the homework? Anything that you needed with number 4? Did anyone else have another one before 4? Anyone else? Okay, so let's take a look at number 4. So one of the things, so remember for a Cauchy sequence, so if you have an epsilon greater than 0, then there exists an n such that for all m and n greater than that n, we have And this one's actually fairly short. We have mn less than that epsilon. So now we can pick, let's say, pick an epsilon. I picked, like, say, 0.25. Then for all n in n, so if we want to disprove it, we'll set that 0.25. Then there always exists, so for all natural numbers, there exists an n greater than n, such that, and you can pick just two consecutive ones. So you could actually pick m plus 1, n is going to be equal to -1, -1 is equal to 2, and that's going to be greater than epsilon. So it's not a Cauchy sequence. So really, that's all there is to that one. Because the idea is, see, you have to be able to pick an epsilon and then find an n such that for all m and n greater than the natural n, this difference is less than epsilon. But see, here we picked an epsilon of 0.25, and no matter what n you pick, you can always find an n, two consecutive ones that when we take the difference, we get 2, and that's going to be greater than the epsilon, if that makes sense. Because so if you can find an epsilon that will never work, then you've proven it's not a Cauchy sequence.
Oh, because it's -1 to the power, so then it's just -1.
Right, exactly. Yes, that's exactly right. That's exactly. And as long as you pick them consecutively, one after another, one is always going to be -1, the other one will be 1, or the first one will be 1 and -1. They'll always add up to 2, an absolute value of 2. And so you can never find an n big enough that you can go out there far enough where you're not going to have at least the difference of 2, which will be greater than that epsilon. And now I just picked 0.25. You could really pick anything. You could even pick like 1 or 1.5, because none of those would have worked. And that epsilon bigger than 2 would work, but we found an epsilon that won't work. Any other questions?